Okay. So definition. The layman's terms, I would just say every input is assigned to only one output, meaning your input cannot go to two different places. So that's the easiest way to think of it. That's the definition of a function. Okay, so if I plug in something, I only get one thing back. So a relation. So here's the more technical definition. That assigns to each element x from a set of inputs or was another way to phrase it, or domain, I guess. The set of inputs is also called the domain. Okay. 1 second. The relation that assigns assigns to each element x from a set of inputs or domain exactly one element y in a set of outputs, also called the range.
Excuse me, sir. I had a question.
What's up, man?
So for the 2.2 that you're doing right now,
Yes.
is it okay if you can actually extend those ones? Because we didn't go over these in class. I don't know if somebody else already mentioned that or not.
No, of course. Yeah. If we haven't mentioned it, if we haven't talked about it, they can't be due yet. So yeah, I'll adjust all that soon.
Okay, thank you.
Yeah, I think it was due a little earlier than it should have been. Anyway, but yeah, thanks. So visually, definition of a function. So this is all the domain values or inputs. And this is all the range values over here. The function is what maps them to the other location. It sends them from here to here. That's what a function does. And a function is a type of relation that fits this definition. Okay. So the easiest one is like, let's say, I don't know, John, Mike, I don't know, Sarah, Sam. Now, let's say all these people have some phone number. I'm just gonna make up some numbers here. These numbers do not matter. You can write whatever you like. I'll write your number by accident, my bad. Don't matter. Should have made that circle bigger. Okay. So each of these people, let's assume most people, right, have just one phone number, one cell phone number. So if John has that number, so the function is assigning people to phone numbers. That's all this is, right? Mike has this number. Sarah has that number. Sam has this number, right? So you see how every single input has only one output. That is basically what this paragraph is saying here. Just visually. Does that make sense?
Yes.
Yeah.
So if you would have seen, like, let's say, I don't know, let's say Sam had two different phone numbers, right? Maybe he's a drug dealer or something. I don't know. That this would no longer be a function, right? Maybe he has like a bunch of girlfriends. But since they all have one phone number, we're good. So this is the function assigning values.
I have a question.
What's up?
So so if Sam if he has two phone numbers, the only Sam is not part of the function, or not all of the function works, or
If it say that one more time.
like if Sam has two phone numbers, is like everything like is dismissed, or only Sam is not part of the function, or
Yeah, it would break the definition or violate the definition, which means it is not a function.
okay.
But it's still a relation. Like, for example, a circle equation is a relation, but not a function. So this is a function currently, but if you violate this definition here by having an input go to two places, no longer function. Oops, I should say outputs right here. Okay, so really that's all we need to understand for this section is what is a function? If that makes sense, this section will be super easy. And yeah, you should be good. So let's look at these ideas here. Let's do a few of them together. Okay. All right, so right here. So determine the relation y as a function of x. Determine if this is a function. Okay. So basically, we have our inputs over here, right? We got 10, 7, looks like that's a 4, 7, 10, right? So
They have to be in order, I guess, or
no, but these are in order here. These are assigned like this. Does that make sense? Those are the pairs.
okay.
It came out a little weird on the screen, so it's hard to tell.
So should we be able to follow along with you because it's not working on the section 2.2 functions?
Oh, you mean you can't open it up? You're saying?
Yeah, it says it can't put anything in.
All right, let me has it closed? Okay, let's get back to this example here. Okay, so we have two sets. So the easiest way that you can spot whether or not it I think we have a circle function here. It's much prettier. If you see the input go to two places right away, that should tell you it's been violated. But let's go ahead and see it. So 10, 7, 4. So you see how 7 is repeated? So if that goes to a different spot, then it's not a function. 3, 6, 9, 12, 15. Of course, you're not going to draw this every single time. It's just so we can see this first time doing it. 7 goes to 6, 10 goes to 3, 4 goes to 9, and all of a sudden 7 goes to a different place. So that is not a function. So that's why it's no, right? Does that make sense? This 7 goes to
Yes.
2, spots right there. And if you look at this one, none of the x's repeat, but notice how they all go to the same place. So you can have all your inputs go to the same place. That's okay. You just can't have your input go to two places, the same input. So this is fine. Just remember the definition. Okay. So here's, or a set of ordered pairs represents functions from A to B. So this is like the first circle and second circle. Do you see any x values repeating? So pretty much safe to say it is a function. They didn't ask us, but if you see nothing repeating, then you're good. Don't worry about it. What they want us to do is write them as ordered pairs. So you pair the first one with the first one, right? Let's see here. Right, the set represent A to B, select all that apply. So -2. Why is this right? From A to B. Yeah, I would have picked this one. 1 second.
Well, why is there a -2 of a 2?
Which set of ordered pairs represents functions from A to B? Oh, I see. Okay. Basically, what they're doing is pairing these with any of these. It doesn't matter. They're not putting them in order like we did up here. Because here they actually specified input and output. Over here, they didn't say anything. So they're pairing them however they want. So as long as we don't violate the definition of a function, we're good. So you pair these, any combination. So what you're looking for here is seeing did the x repeat? No, right? For this one. Over here, did the x repeat? Any of the x's repeat themselves? There's a -1, -1, right? So you say, no, this is not a function. Over here, they didn't have all the elements. They're missing some. So it has to be this one or this one. These don't violate the definition. This one does not represent A to B. Do you see why we're choosing A and C?
Yeah, the x doesn't repeat.
Yeah, and that'll keep you straight for the definition. If you just look at the x values, you'll be good. On these, you're gonna have to do some work. You can graph it and see it. I think, let me see if they talk about it here. It might be next section. It's a little long. I might trim this up a bit for you. It's too much. Okay, number 8. Okay, first example here. I'll switch in a second. Determine whether the equation represents y as a function of x. Okay, so if you try to solve for y, right, then you will see if it's a function or not. Currently, it's not in that form. Y equal to something. So subtract the x squared. Square root both sides. Remember, we have to tack on the plus or minus over here. So the fact that you have a plus or a minus is pretty much going to be the reason it's not a function. So if you let's go ahead and graph it so you can see the reason.
But can't you can you put like the 3 and the x like outside the radical?
The no, oh, for the 9?
Yeah, and the x squared.
No, only if it was factored out. Like if it was 9 times x squared, then yes. But not the minus or plus. So this is the positive version. So if you type this again with a minus, right? You can see that you have 0, an easy one, going to 3 and -3. See, all these numbers, all these x values are being mapped on the bottom and on the top. So there's many points that violate the definition. I think later we'll talk about how if you can draw a vertical line through any graph, and if it hits more than one spot, or if you draw just any line like this, if it hits more than once, it violates the definition, not a function. Okay. Which we'll talk about later. Anyway, where was it? So this is not going to be a function because visually it violates. And if you plug in some numbers, you're going to have, you'll see that it'll be mapped to 2 different places. Okay. So the easiest way to see is just to graph it, in my opinion, just see it. You can also plug in numbers, but that's a little more work. Okay, give me a second. Let me make a note of that before we move on. Not a function by the vertical line test. This is what I'm just going to write down what we just said. So if a vertical line intersects a graph in more than one location on the graph, then the graph is not a function. I think that's how I want you to approach it. Just graph it.
So how would we know when a given equation is actually a function? Is it when it gives us any value?
What do you mean? Like,
So if it's like y equals a number, x equals a number, what actually defines a function? If we were to solve all these equations, right,
Mhm.
on paper without using Desmos or anything like that, and to do the vertical line test, what answer for the equation?
if you would have to graph it by hand and then see it.
Okay.
Because you can always graph this. I mean, you should know since we talked about it before, this is a circle.
Mm-hmm.
You should know that no circle is a function because you'll always intersect it more than once. If you try to solve it, this plus or minus is going to violate it because you'll have two different outputs with the same input. So for example, if I plug in 0, you see that I'm going to get plus or minus 3.
Yeah.
So that right there is a violation because I have 0, 3 and 0, -3. So you could plug it in, you could plug in any number and it'll come right out, has 2 values. So that can be an alternate way if that's what you're asking.
Not really for this equation, not specifically. But other ones that are functions. But I guess we'll get to those ones soon. So maybe that'll answer my question later.
Yeah, I mean, if it is a function, you'll see it graphically right away, but also you'll only have one output for every value you choose.
Okay.
Like for example, if you can't solve for y, most likely it's not a function. If you get a plus or minus, it's not going to be a function. If you have a circle, of course not. Those are the obvious ones that you should see, but almost everything else will be a function. Like any line is a function unless it's vertical, right? Obviously. Oh shit, my hand. Let me show you here. So this guy right here, if you solve for x, you notice how there's no y part.
Yeah.
This will be a vertical line automatically. X equal to a constant is a vertical line. Y equal to a constant is a horizontal line. So this will be fine. This will not be. Any other type of line will always be a function. The only one you got to worry about is if there is no y value, because that'll graph vertically like this. So x equal to any number, let's say 2, right? It's always going to be vertical at that location. So it violates the definition, right? Y equal to anything will always be horizontal. These will be fine, but any other line, any parabola is always a function. But graphically is the easiest way. Plugging in numbers, you could do it that way. There is, I think, in the book an analytical technique that you can use, but I don't recommend it. I don't think I have the book open. Let's see if I can find it. Two. Okay. Wait, I think this is the wrong book. Damn it. Oh, here we go. All right, so we talked about the definition. I don't think they talk about it here.
Oh, I have a question.
Sure, what's up?
To what math class do you start doing like math projects or like investigating and that stuff?
Uh, maybe in calculus, maybe in discrete math, you might have some as well, um, depending on the major.
Okay.
Okay. Trying to find out if they have an example like what you were asking here.
I have a question.
Mhm.
When is our first test? What is the date?
We'll check in just a moment. I think it's this week or the end of this week. But let me check, give you a hard
I
date.
thought you said the test was October 17th.
Was it? I mean, whatever I said is probably true, but I gotta check the actual thing. Give me a second. Just go check. Yeah, I don't think they have those types of problems here. Okay. Schedule. Technically, the test should be done anytime during this week. But I think I set a specific date up here. Oh, wait, I remember now. We combine the two things together. Yeah, October 17th. That's what somebody said, right? Yeah. So
Yeah,
It-
because that's what you said. I asked that same question. You said October 17th.
yeah, it is October 17th. I just forgot. Sorry. We did mention that. Okay. Yeah, let's get back to it there. 1 second. I'm gonna close Discord and bothering me.
When we do the lockdown browser, is
Mhm.
it just like the homeworks browser where it's like randomized all the questions and stuff like that?
I think it's like just a specific it's not through Sengaze or anything. It's just inside Canvas.
And it's like a test format that you give and it's like static.
I think it randomizes the questions, but it's a little more static than the what's it called? Homework.
Okay.
Let me see here. All right. Sorry. Got sidetracked there. Okay. So first few, I say just graph them either by hand or on paper, or think of the type of function and then determine. So remember, I would try to look up the parent function so you know what each one looks like, which we'll talk more about in the next section. I think that'll help a lot. So after that, after applying definition different ways, they're just going to want you to understand this notation. You see how right here, they're saying f parentheses 1. That means plug in the 1. So anywhere you have an x, f of 1 is how you read this, will be equal to 3 times 1. There's no more x's, so just minus 4 there. So the result will be 3 minus 4, right? Which is -1. So that's all you're going to do here. You're going to plug in the number, plug in this number. Technically, this is an x plus 2, but you treat it just the same. Okay. So if we were to do that, you would do, let's go and do it on paper so we can have it. 1 second. So so we're comfortable with notation. Find the functional value if possible. So in this example, this is problem 15. They give us a function equal to 3x minus 4. So part A says f of 1. So that means 3 times 1, right? Part B says f of -3. So 3 times -3 minus 4 would be, let me fix this a little bit. Plug in -3 goes into that specific x. 4 looks like garbage. Let me fix that a little bit. So it'd be -9 minus 4, which is -13, right? F of x plus 2. So whatever is in here, that is what you're going to plug in. I don't care what it is. A triangle, a square, w plus 7, doesn't matter. You just plug it in. Don't ask questions. Just plug it in. That's what this notation means, right? Once you plug it in, you do your math. So 3 times x plus 3 times 2. Then I'll get you to here. So 3x, 6 minus 4 is 2. So this is the result of that input. The result, the output. Given these inputs, we have these outputs. Okay, so the x value is 1, -3, and x plus 2, I guess, which is weird. The y values, quotations, -1, -13, 3x plus 2. Does that make sense? Right, the x values are your inputs. The y values are your outputs. But after a while, we stop calling them x values and y values. They're just inputs and outputs, domain and range. Doesn't matter what the letters are. Okay. So as you can see here, 16 is the same type of deal. They give you a different function, plug in the 2, plug in this. So just make sure you follow your PEMDAS, right? And you'll be good. Because you're going to have to FOIL this out, t minus 2, and distribute the 8, etc. Does this seem doable? Does it seem okay? Have any questions on 16? Or does it make sense?
So for the 16 we would what would we file there?
Man, let's go ahead and do it.
Yeah.
Just in case, right? In case it gets hard or something. Okay, so same instruction as number 2. Problem 16. Okay, so g of, I'm going to change it to x because my t's are garbage. 5x squared minus 8x plus 6. The part A, g of 2 equals 5 times 2 minus 8 times 2 plus 6. So no big deal here, right? This would be 5 times 4, 2 squared, minus 16 plus 6. So this will become, what, 20? No, 10. This one, though, is a little weird. We're going to have to FOIL this out. So x minus 2 squared minus 8 times x minus 2 plus 6. So this will have to be multiplied correctly. So this is technically 2 of these, right? distribute the 8, that'll be 8x plus 16 plus 6. Right, that's just this distribution here. But this multiplication is going to give you a trinomial, right? X times x. The 5 will happen after. I'm going to put brackets so we don't get confused. X times x. X times -2. -2 times x. -2 times -2. So that's in there. 16 plus 6. 22, right? Yeah. Combine these like terms. Change the parentheses for no reason. Okay. So far, you guys with me, right? I'm plugging in x minus 2 into the function here. So wherever you have an x, you're going to have that input. Just like on this one, we had a 2. So everywhere we had an x, we got a 2. But this time our input is 2 terms. So when we multiply this out here, we get this trinomial. Distribute the 8, we get this 2 terms. Combine these two, we get 22. Now we have to distribute the 5. So 5 times this, 5 times that, 5 times 4. Combine like terms one more time. -20 minus 8. 20 plus 22. So this will be the output here. Any questions about any of these steps? Okay, so far you're comfortable with the notation and you can plug in anything without problems, right? It's not weird. All right. So see, it's more of the same, just different types of functions. Okay. Over here, we have something different. We have a piecewise function. So basically what they're doing is they're taking 2 different functions and gluing them together around these parts. That's the easiest way to think about it. So it's this line. You're graphing this line as long as I'm less than 0. I'm going to graph this line as long as I'm greater than or equal to 0. That's how you should be reading this. Okay. 2x plus 1, 2x plus 2. So think of them as 2 separate functions. Okay, that's what it was. 2x plus 1 and 2x plus 2, right? Yeah. So it said that it's going to be plus 1 when I'm less than 0. So plus 1 is the blue one. So from here down is the function they're talking about. Then as soon as it gets to here, it jumps to this function. So these 2 are the ones we care about. I'm going to graph over it so we can see better. I'm going to use red. So picture, this is the function they're talking about, right? The piecewise function does this graphically. It goes from -infinity all the way into 0, and then it changes to this other equation and jumps up here. Let's make sure it didn't mix that up. May have. 2x plus 1 less than 0. Yeah, so 2x plus 1 is down here. When it's less than 0 on the x's, we're at this red part. When we hit 0, this is technically an open circle. It jumps over here. This is a full circle and then keeps going. So this other stuff, just pretend it's not there. The green and blue are non-existent, okay? Only the red. The red is this function they're talking about. So this is the graph of this function here. Does that make sense with how they did this? So this right here is the function, the line 2x plus 1. This one is 2x plus 2. So when you were greater than or equal to 0, we switch to this line on the function. If we are less than 0, we're going to be on this line. So they're connecting two different pieces, right? That's why it's called a piecewise function into one function.
Is it always going to be a diagonal or?
Now you can connect any function you want. You can have a parabola and a line. You can have a point and maybe a cubic function or a square root function and a line. It doesn't matter. This first one is just two lines. See in number 20, they have a line and then they have a parabola. So you can use you can have two different types. But so visually, that's what's happening. Does that part make sense? We haven't really got to the question yet. Okay, I'm assuming that makes sense. So now let's look at the question. If f of -1, okay. So -1, you agree is below 0, right? So I should not be using this bottom one, should I? Because this is greater than or equal to 0. So since -1 is below 0, you would plug it into the first piece. So for part A, you would use this one. That's how they get this answer. Does that make sense?
Yes.
On part B, they're plugging in 0. So we can't use the first one anymore because it needs to be less than 0. But this other one says equal to. So we're going to use the bottom function for part B. So you would do 2x, 2 times 0 plus 2. That's how they get the answer for this one. So for f of 0, we would be on this line over here. For f of -1, we'd be down here somewhere. Okay. F of 2, well, that's also greater than 0, so you would use the second one again. That's how they get 6. Is there any questions with the inputs or the graph? Do you see how a piecewise function works?
So you just have to decide which one to use.
Yeah, based on the restriction right here. This is it's kind of telling you like where this is telling you where this function lives, right? Below 0, we're living over here. We're using this one. 2x plus 2 lives above 0 or equal to. And any other questions?
So when you're getting those two red graphs, or can you hear me? I'm sorry.
Yeah, of course.
Okay. When you're getting those two red line graphs from
Mhm.
just the 2x plus 1 and then the x is less than 0, is that how you, I mean, that's how you're coming up with the graph without plugging in the -1 or anything like that, just the graph. On the
Um,
2x.
Yeah, we're using this restriction to graph it. So if I was to graph this by hand, right, you would plug in a 0 and then a number below and connect the two
Oh, okay.
dots, and then but leave a hole open for 0 because technically it's undefined here at 0. On this one, you plug in a 0 and then when any number after and connect those two dots. So at 0, I would get 2. If I plug in 1, I would get 3. So I just connect those two lines here. But we can. You want to graph it by hand? You want to see it?
Sure.
Okay, let's go ahead and do it. So they gave us number 19. So piecewise, if you were doing this by hand, you need to be comfortable graphing functions. Example 4. Let me switch over in a second. Okay. So if we were to graph this, you can plug in any numbers you want, but we need at least 2 points to graph each line. So I'm gonna put 1, 2, 3, 4, 5, -1, -2, 1, 2, 3, 4, 5. Might need a few more, but it's okay. It said this one must be below 0. This is where it's located. This one's equal to 0 or above. It's good to use a restriction to help you graph it. So if I plug in a 0 into the first one, right? So let's make like a big table here. I'm gonna come back to that. If I plug in 0, technically I'm not allowed to plug it in here, but if I did, you notice that you would get 2 times 0 plus 1, which is 1, right?
Yes.
If I plug it over here, you notice I'm going to get a 2, right? Okay. If I go to that location for 2x plus 1, it would be 0, 1, right? Now I can use anything below there to graph. If I use -1, that would be 2 times -1 plus 1, which would be, what is that? -1, right? So -1 would be my other point here. So since I have to go below, I can go up. This is the 2x plus 1 line,
Okay.
right? See what I mean? Using these 2 points.
Okay.
Now I can use, now to graph the other one, I got to be at 0 or above. So 2x plus 2, that would be right there at 0. If I plug in, let's say I plug in 1, that's above 0. That would give me, for this function, 2 times 1 plus 2, which would be 2 plus 4. Yeah, okay. So 1, 4 would be here. So here's that other line. So these are the 2 red lines I had earlier, if you graph by hand.
Okay. So it's being determined by that x is less than 0 and x is greater than or equal to 0.
Yeah, that's basically, this tells you where to graph the top line. So that's below 0, but technically not defined there because it wasn't equal. The only reason I plugged it in was so I can have a starting point. So it starts right below there. This starts right at this point for the other line.
Okay. I got it. Thank you. Appreciate it.
Yeah. That's how you would do it by hand. But they didn't ask for any of that. They just wanted you to plug in the numbers, but I wanted you to be able to see visually what's happening because it helps to understand. Okay.
Yeah, I'm the worst at graphing. So yeah, but thanks.
Yeah,
It
it's
helped.
okay. You don't have to. I don't think it's gonna come up here anyway. But yeah, if you want to use your graphing calculator or Desmos, it's fine. I'll leave that one to you. So any questions on this idea of a piecewise function? Okay. Let me delete some of these. Okay, let's talk about domain. So remember we said domain is a set of inputs. So they want to know what are all the input values of this function? In other words, what is everything you're allowed to plug in without any issue? That's the easiest way to think about it so you can find them. So if you look at this parabola here, is there any number you can't square and times 3 and then add 2 of that number minus 4? Can you think of a number that would cause problems by plugging it into this function?
Zero, maybe. I don't know.
0.
If you plug in 0, these would disappear, right? And then you get a minus 4. So 0 is allowed. There, I don't see any issue here at all. And if you doubt it, you can graph it and verify. 3x squared plus 2x. 3x squared plus 2x. Is it minus 4? Yeah. So look at it yourself, right? There is no holes. There's no asymptotes. There's no problem. So you can plug in any x value you want. Right? It goes on forever. So this can, no matter what x value you choose, you're going to map onto some y up top. So 3 will be okay, 4, 5, forever. You'll keep plugging in numbers. Okay. Let me see if I can adjust this. All right, you see how you can keep mapping it to infinity? They'll keep hitting a y value over and
Yes.
over again in both directions. So there is no x value you cannot plug in. Any x value is fine. The domain here would be all real numbers because there is no issue. If you spot a problem, that will determine your domain. If there is no problem, then you can plug in whatever you want. Hence, all real numbers. So the way to find a domain is look at the function and decide, is there any value that will cause issues like division by 0 or a negative inside of a square root, those types of problems. Anything else is pretty much fine. Look at number 26, right? Looks at some point, it's going to become negative inside, right? What is the lowest number I can plug in there? The most negative value.
Would it be a -5?
Yeah. If you plug in -5 plus 5 is 0, right?
Yeah.
Zero is fine. You can have a 0 inside. So anything that results as a negative inside is a problem. If you plug in -6, what would happen inside here?
Yeah, you get the -1.
Yeah. So if I were to say, let's just write it out in case you don't see it. -6 looks like a B, but it's a -6. So that'd be square root of 6 negative plus 5. The result would be a problem. So this is why I must stay above -5, because -5 results in a 0. -1 is a problem. Anything below -5 is a problem, even though decimals. -5.1 is also an issue. Yeah, this would be complex or imaginary, so it's not in the domain. Another way to think about it, does that make sense though before I change that idea?
Yeah, makes sense.
So another way you can think about this is say, you know what, I need the inside to be positive. It needs to be greater than or equal to 0 because that is a restriction of a square root. Do you agree? This needs to be true inside. So if you solve for y by subtracting then 5 over here, you would get the actual answer, the domain. So when y would be fine as long as it's greater than or equal to -5. So you can solve for it and get this answer anyway. It's another way to think about this. You think of the requirement and then you solve around that requirement. Does that make sense?
Yes.
Yes. Yeah, instead of taking the radical, you do the greater than or less than equal to.
Mm-hmm. Yeah, and just make sure, just remember the inside must be greater than or equal to 0. You can also graph it and just look at it. Let's think, is it 5 minus 5? Yeah. I'm gonna use X just cause, who cares? So here is the square root function. Notice how it goes on to infinity, right? Forever. But the lowest point that I can have is 5. As we were saying earlier, if hold on. Y plus 5, yeah. Mine was plus. There it is. So the lowest we can go would be -6, or -5 is the lowest one. So graphically, you can see the domain starts at -5 and it goes on forever. So using interval notation, you would say, oh, okay, that starts here, goes on till infinity. So that would be the answer for your domain in interval notation. Anyway, does that make sense? Yeah, they just put it in plain English. So
So when are you gonna have that open circle?
when you can't include it, like for example, this one here is a good one. Let's do that by hand. 28. x squared minus 4x. So if you were to factor this on the bottom, you would see that there's two problems, right? Because when you have a rational function like this, you cannot have 0 in the denominator. So what you could do is set this bottom part to 0 and find out when that happens. So once it's factored, you can set each part to 0. So there's not much work to be done. So we're going to have problems when x is 0 and when x is 4. So they cannot be 0 in this case, right? So the domain would tell you you can have any other value except these two. So visually on a number line, there's a problem at 0. There's a problem at 4. Everything else is cool.
We're not supposed to do the conjugate.
What's that?
The conjugate.
Conjugate. Oh, no, not for this one. Are you talking about the difference of squares? It looks like it, right? But so what you want to do is create a domain that excludes these two holes. Okay, so parentheses always goes on infinity. So negative infinity all the way until 0. So I'm going to go up until 0, but it cannot include it, so you leave it open. And then you go from 0 to 4. These will be open. Everything after 4. So you see how I put parentheses? Because they cannot be equal. If I put a bracket, that means we're starting right there. Parentheses means I'm starting right after. That's the big difference. Are there any questions on this idea?
No.
So to answer the question, right, in interval notation, you would say, all right, well, this first part unioned with the second part, unioned with the last part. So these three pieces is how you would represent everything except these two spots. But you can also do it this way. Just in plain English, right? X is 0, X is 4. Everything except those two spots is technically the answer. But if they ask for interval, the way I did it is how you're supposed to do it. Any questions on that?
No.
So whenever you're doing domain, think of what are the problems, figure out where those issues happen and exclude them. Everything else is the domain. That's all you got to do. So look for division by 0, look for even roots that can't have negatives. And if both of those things happen at the same time, well, then you're gonna have to exclude both at the same time. Like number 29. Notice how I can't go below 2. And I can't be equal to -2. It can't go below -2 on the bottom or the top. Let me think. No, I'm sorry. Inside the square root, I have to be -2 or higher. But down here, the only issue is -2. So I have to exclude -2, even though it's okay on the top. It's not okay on the bottom. So that's why they say everything above -2 is cool. Because if I go below this, I get negatives in here. And if I go equal to it, I get a division by 0. So this takes into account those two problems. Here we only had to worry about the bottom. Over here, we only worried about the inside here. Anyway, let's move on to something else. Let's talk about this here. This is called the difference quotient. So I need to give you that formula. And that'll be it for this section. Okay. Example 6. Find the difference quotient. So this is not difficult, it's just tedious because it's algebra heavy. So that can be hard if you don't know if you're a little rusty on the algebra. But the idea is just a formula. So this is the difference quotient. Give you the formula first. Difference quotient. So you take the function and add h, then you subtract the original function and then divide the whole thing by h. So we can do this in steps. So step 1, f of x plus h. Let's do that first. So remember how we said that just means you plug it in. Don't overthink it. Just plug it in. Distribute 3. Okay. This will require us to multiply. So you multiply this out. That'll get you to x squared plus 2xh plus h squared. Distribute that nonsense. Negative 3 times this, negative 3 times that, negative 3 times this. Okay. So just going to slow down for a second. 3 times x, 3 times h, give me these two terms. FOIL this out or multiply this out, gives me these three terms. Multiply by negative 3 gets me these new terms. All right, all I'm doing is plugging x plus h and simplifying. That's all I did. Combine like terms. I don't see any. So I'm just going to put them in order and move on.
So what goes first, the h or the x squared?
The x.
Okay.
That doesn't really matter. There's a lot of different variables. Okay, step 2. You subtract this result by f. So you take all this result here. Subtract by the original. All right, this is subtract by f. So the formula says, so here's my f. And then cancel your like terms. Distribute the negative. So notice how the x squares will cancel. The 3x's will cancel. That'll leave me with negative 3h squared minus 6xh. So that's step 2. I took the result from the part step 1 and subtracted f. That's what we did. Simplified, terms canceled, we got to here. You guys okay so far? So if we do it like this piece by piece, it might be a little easier instead of all at once.
Yeah.
Step 3 is divide the result by h. So we just got Let me know if I'm losing you at any point.
So the h doesn't have a value or
Currently, no. Later in calculus, it'll mean something, but right now it's just this is a difference quotient. So we get the top part. That we got from the first piece, and we'll notice that the h is going to cancel. So the value is not going to matter. So factor an h out from the top. Divide by h. So the answer would be this here. This is the difference quotient. So this right here is equal to negative 3h minus 6x. Is there any questions about any of these steps or any of the algebra?
yeah, I guess we have to be careful to like the last step you factor it before like canceling the h.
Yeah, just make sure it's you factored in order to cancel. Oh, I made up my own question. Oh well. I'll check it out. Their question had no 3 here. Theirs was easier, but oh well. But yeah, that's pretty much it for this section. So the main ideas are, do you know what a function is? Can you determine if something is a function based on the definition by looking at the inputs and outputs? Can you determine by looking at a function and its graph? Can you deal with plugging in values into a function? Can you plug in values into a piecewise function? And can you find domain and range, or find the domain of functions that they give you? And then the last thing was that we just did, find the difference quotient. So those are all the main bullet points for this section. So let's see, we're going to go ahead and stop here. Do you guys have any questions about this section or in general, any issues you're having?